Julie said, let's see here. I'm Don Gillis. I work in educational services. I'm one of the trainers there. I work under Ben Weezer. Today we're going to talk about CO2, but what I wanted to do is I was going to hit on high ambient temperatures. But by the way, if you're an Emerson employee and you just got done seeing Andres, this is going to be very similar to that. Okay, I don't want to bum you out, let you down here, but we've added quite a few people since a couple weeks ago, so I want to start a little bit at the beginning and just get some terminology out of the way so we know what we're talking about on the critical point here a little bit. Okay, so bear with me here. Slid this slide in last night, just some of the products that we have on the CO2 side, the A bulletins I highlighted at the bottom there, and I'll bring those back up at the end of the presentation also. So on the left-hand side, just so you know, you can see how many bolts are here. This is a transcritical side. This is going to see all the high pressures, 1700, 1600, somewhere thereabouts. You can see there's a relief valve plugged in the side of it there, installs. This is going to be our subcritical compressor, our ZO, at the bottom on the low temperature, and you'll understand that hopefully a little bit better as we move along. This is our trainer that we travel with. Actually, this is Andre here and Elaine Mongrain, who usually works with me in the States. This happened to be a class up in a refrigeration company called AAA up in the New York area. Okay. I'm going to talk about just, again, some of the basics of the terminology at the very square one for those of you that weren't here a couple weeks ago, and refresh for the rest of you. So CO2, again, has a global warming potential of 1. This is just a side-by-side view. Just going to kind of go through this fairly quick. If it's in red, again, it doesn't do as well. If it's in black, that means it's better in that application, okay? Some of it, like this here, for the inert gas, flammability, toxicity, odor, it's pretty much neck and neck the same, okay? High ambient performance doesn't do as well in transcritical, and I'll get into what transcritical means to us here in a little bit. And then the complexity of the system is going to be much greater. As of right now, the adoption is low. I see that changing quite a bit as time goes on. More and more people are going to CO2, especially with some of the regulations that are coming down the pipe for supermarkets or larger applications, okay? Again, CO2 is a natural refrigerant, obviously. It has a global potential of 1. I'm not going to go through the whole thing again, but everything is based off of CO2, okay, and it is a ratio. So if you see a global warming potential of 404A, for example, is 3,900 or roughly thereabouts. It's 3,900 and some pounds of CO2 is the equivalent of 1 pound of 404A of the damage it does to the atmosphere. Atmosphere comprises of approximately 0.04% of CO2, and therefore it's a great application for us. Now, here's where we get into the basics of it for the most part. Temperature at atmospheric pressure is a -109, very, very cold, obviously. Not that the other refrigerants aren't cold, but extremely cold here. Our critical point is 87.8. So, in other words, and again, for those of you that saw this a couple weeks ago, or this section of it, bear with me. This means when we hit that critical point, it has a very, very low critical point. All refrigerants have a critical point. We just typically don't see it. In layman terms, the critical point, all that's telling you is the ambient temperature outside. So if it gets above 88 degrees, it doesn't do as well. And I'll explain that to you in a little bit. And that's why I want to get into the strategies of high ambient and what we're doing about that to make it easier to install in some of the hotter climates, okay? Critical pressure at 87.8 is going to be 1056 or 1055. That's PSIG. Obviously, at PSIA, it'd be around 1070. Triple point is going to be 61 PSIG. Again, we have a very low critical temperature, and we have a very high triple point pressure, where all three of the gas meet in that area. So in other words, when we charge a system, we have to make sure that we're way above the 61 PSIG. We cannot go in with liquid right away. we get the opportunity of having dry ice. Okay, so we have a solid, liquid, and a vapor at the 61. I'll show you a little chart here in a little bit. Okay. Pressure temperature relationship, again, a very high triple point, a very low critical point. You can see what we're talking about here compared to the rest of them, 404A, 134A, 717, okay, above the atmospheric pressure. That's why it's a little more complex to use as a refrigerant. And by the end of this, hopefully you'll understand a little bit better. Again, minus 109 at the temperature, atmospheric pressure, very, very cold. The real thing I want to show you is here, this is a filter that we took off. This is actually air exposed to a liquid refrigerant. It immediately turned into dry ice, okay? The liquid CO2 exposed to air will cause dry ice. So it's very, very cautious as we have to be careful about moisture like we do in any refrigerant, okay? It causes carbonic acid, which will eat away anything it comes in contact with. And something I didn't touch on, or maybe I did last time, was we're talking about we must use a Coleman grade or a grade 4, we refer to that as. It has less than 10 parts per million of moisture, okay? You can use a better quality, but not less quality, okay? One more time, again, to recap on some things we talked about a couple weeks ago, probably one of the most important things that I found out about CO2 when I started training a few years ago under Andre and Alain and some of the other Canadians up there that our Emerson team. CO2 expands 845 times going from a solid to a gas. It's sublime, so it doesn't go from a solid to a liquid. It goes directly to a vapor. So in other words, 1 liter of dry ice will produce 845 liters of gas at 14.7 atmospheric pressure, okay? The relatively vapor density versus air is 1.52. So a couple of demos I talked about a couple weeks ago that we do in class is I mentioned that we take the Tupperware and we'll put 1 cube of dry ice in it, 2 cubes, and then 3 cubes in 3 different pieces of Tupperware. And we'll show the students how they'll go off one at a time. Obviously, the one with the most dry ice will blow up first. It almost looks like a capacitor. If you've ever seen a capacitor go bad, it starts to dome the lid and then pops it, okay? So you'll see and then on the 152, what we'll do is, what I do is put a piece of dry ice, like you do at Halloween, if you will, into some warm water, and you'll see that gas drop down here as it goes. And it gives the technicians a good visual of what that's going to look like. So the moral of the story is we're probably going to, not probably, we will have our alarms at around 18 inches or lower off the ground. We talk about CO2 being non-toxic and non-flammable, but with it, like anything, so many parts per million, it can asphyxiate you. So in certain areas, you will have to have ventilation. Dry ice is formed by a solid, or 744 is the refrigerant name for it. The deposition is dry ice formation. Sublimation, again, is conversion of solid to a gas. And again, it is a ratio of 1 to 845. This is just going to show some enthalpy charts, and I'll walk through these with you. Anything, so here's our critical point. Again, it's talking about our temperature. This is our two-phase area. At 87.8 is the last point to where we have liquid and vapor together. Above this, we have a supercritical fluid, okay? The PT charts no longer work. So if you were to go to PT Pro or any PT chart with CO2 on it, you would see that it would stop at this pressure, 1055, at the critical pressure, okay? So anything below this, again, is our subcritical area. I touched on this the other week, a couple weeks. I don't know how many of you benefited from it, but just in case there's somebody on the line that doesn't understand these real quick, this is actually what I'm going to walk through this. This line indicates your compressor. This line on an enthalpy chart indicates your condenser. When you're vertically coming down, this is showing you coming through the metering device, and then this is our evaporator, okay? As I said last week, this will be your bubble point over here on the liquid side, and this will be your dew point as you're leaving the two-phase area. This is just showing you above the 87.8. Now we're in PSIA again, 1070. We're pushed above that. This will be the transcritical cycle, okay? And this, again, is where we start to lose some efficiency. When we get above that, you can notice how narrow our enthalpy chart gets over here in transcritical as it does in subcritical, okay? And then at the very top, I wanted to show you what that looks like in all three stages. And this is as I know Andre mentioned earlier, in a lot of applications we'll purposely push that, even if it's in subcritical, in a lower temperature area to utilize that for reclaimed heat, reclaimed humidity, and for dehumidification and heat and water is the other thing I wanted to talk about. It looked like a question came through, Julie. I'm not sure if I should move along or. I'm going to move along and then.
No, I'm not seeing any questions that have come up in the chat. I was just looking. It might have popped up on the side of your screen. Go ahead.
It did. All right. This just wanted to point out to you again, this book is something you can get. I know Julie was going to send them out. You can actually put this exact verbiage into your Google machine, and this will actually has a nice copy on there if you ever run low or you need some copies of this. Okay, very, very good book. It's been compiled by the Emerson team. It started out in Europe, and now it's been, as Andre says, Americanized, if you will. This is just showing us pushing that into transcritical. Much more net BTUs in subcritical mode versus transcritical, obviously. Again, as long as we're not seeing that 87.8, we're doing in the subcritical. It's very, very efficient gas. And I'm going to show you a little bit later what those pistons look like compared to, and I wrote on some of them so you can get a visual of what that looks like if you've seen a piston from like an HFC compressor before. I'm going to look at some of the system architectures for natural refrigerants. We have secondary, which means we're using a fluid on the bottom half, and I'm going to show you what that looks like. We have a simple Cascade system, which we're all familiar with. Retail Cascade is simply talking about we've got a medium and low temperature and possibly using the refrigerant also to condition the space, air conditioning.
Hey, Don, we did have one question or comment that came in to explain the difference between transcritical and subcritical.
Okay, very good.
When you get a chance.
That's all right. No, let's talk about it now. So the difference between subcritical and transcritical is this simple. As long as the ambient temperature outside is below 87.8, it is in subcritical. Okay, the pressures are very low. So I'm glad you brought this up because I skipped over it. So, and I normally talk about this immediately when I teach CO2 because it's pretty much foreign to a lot of technicians that come to the class. And sadly, a lot of them are already installing it and they're learning on the fly, if you will. So to put it in layman's terms, subcritical is no different than pressures you would see with 410A in air conditioning application, okay? So 400 or 500 pounds on the high side. So that's kind of everyday business, something we're familiar. I like to share that with the class simply because it takes that fear out of what CO2 is going to do. Now, when we get above that 87.8 degrees or 88 degrees, then we're going to see a much higher pressures, okay? And I'm going to show you what that looks like in the different applications of how we can get away with this. So if we have a low temperature and a medium temperature application, for example, in a Cascade system, the low temperature will only see subcritical because it's condensing on a brazed plate heat exchanger, and I'll show you that here in a little bit. Retail transcritical, again, is just a transcritical booster. Whenever we say transcritical booster, you immediately know that it's designed to go in transcritical, and it only has CO2 refrigerant in it. So as soon as you hear transcritical booster, it means nothing more than CO2 throughout the whole system, okay? And it is designed to do that. When we talk about retail, we're just simply saying we've got a medium and a low temperature application and possibly conditioning the space inside the building, okay? So looking at the left-hand side, this is the typical today's HFC systems, traditionally called a DX or direct expansion. We have the HFCs on the top, HFCs on the bottom, 404A, for our medium and our low temperature. The middle here is a partial CO2 cascade system. In other words, what's going to see our high ambient outside is going to be our HFC. Here we have a brazed plate heat exchanger. Therefore, CO2 above 87.8, when it gets into that high ambient outside above 88 degrees, it doesn't do so well. It's not efficient. So here, we're using a brazed plate heat exchanger, removing the heat as the condenser, okay? So it's not seeing outside ambient temperature, all right? So it's still in subcritical. And again, we want it to stay in subcritical for the most part because that's where it does its best work, okay? And then we have the new kid on the block, if you will, not necessarily, but to most people it is. And now we have the frozen, the low temperature and the medium temperature at the top at CO2, okay? So this also can be, even though it's a transcritical booster, we can also be in subcritical still here on the medium side as long as it doesn't get above 88 degrees, all right? So I'm going to talk a little bit. I've got a slide or two on secondary, cascade, and transcritical boosters. Again, this is probably a refresher for a lot of you. For those of you that missed it a couple weeks ago or didn't see Andre's presentation, this may be new to you for the first time. Secondary, when we say secondary, we're just using the CO2 as a fluid, similar to glycol. Glycol, you'll see this over here. We've got a medium temp application. We have a low temperature application, okay? Over here, we're using glycol being pumped around. I'm going to cut over here to the CO2. The benefits of CO2 is, unlike glycol, we can also have latent heat, remove latent heat, which is huge, okay? Our pumps are going to get smaller. This is probably, just to throw something out there, this pump is probably about 1/10 of the horsepower we would use for glycol. Again, the refrigerant lines are going to get a lot smaller. The CO2 secondary is far more efficient than glycol. I just put some numbers down here. I know some of you saw this a couple weeks ago. 100 to 130 BTUs per pound of latent compared to glycol at 0.8 BTUs per pound. The left side is we used a lot in Ontario, Canada. The glycol used for medium temperature heat exchanger and CO2 for the low temperature. And again, we're using this to condense, all right? You can see where we're at with our pressures, the 200 to 400. I'm going to talk a little bit about the Cascade systems. I think we're all familiar with those, the DX systems. We're going to have the high stage is going to be either an HFC or possibly an ammonia. Again, we're only seeing the temperature here. We're condensing in the heat exchanger here, so it's not seen outside ambient. The low stage provides the cooling load. It uses CO2 and is always subcritical. Okay, the high stage absorbs the heat from the condensing CO2 cascade heat exchanger. The CO2 condensing temperature is always below the critical point. Okay, the high stage is usually a simple closed couple system. Now the condensing temperature I noted here is relatively low, possibly 30 degrees. We would need to insulate these liquid lines also. Low temperature CO2 retail cascade system. Again, now we've added a medium temperature application also. We're still using the HFC or ammonia at the top. This is probably the most common application that we have right now in the higher temperatures. even in the States. This is kind of a good way for someone that's curious about CO2 to kind of get their feet wet, if you will. If they're not sure about going all the way CO2, we've still got a little bit of HFCs here removing the heat again from the CO2. So we're not seeing outside ambient. So very, very good in low temperatures. Utilize CO2 as a direct expansion, and display cases, freezers equipped with the electronic expansion valves. Again, CO2 is very hyperactive. So when we use CO2, we're going to see everything modulating, mostly all electronics on everything, okay? There's a little notation I put in here, the difference in pressures between the suction discharge and the cascade. This is our low temperature again. Look at this, again, compression ratios usually in high are 3-to-1, somewhere thereabouts. Medium is 5-to-1. Low temperatures typically somewhere around 10-to-1. And you can see by the math here, let's take the 200 to the 400, we're less than 2-to-1 on the compression ratio. So that is huge with the efficiency of the compressor. It's not working very hard, obviously. Okay, here's some pictures I took yesterday of a piston I have here at the house. I measured it out. You can see this is for a 50 horsepower CO2 system. You can see how wide it is. You can see the connecting rod, how large this is. The shaft's still large, but the piston of the CO2, because of the efficiency, is very, very small. Okay. Talk about the transcritical system now. Again, when we talk about transcritical, we are talking about a system that's designed to go into transcritical. We know it's going to hit 88 degrees. It's designed for that. Okay. Some of the system challenges, the design to max conditions, the capacity control, the multi-compressor, compressor unloaders, and the gas bypass, and so on and so forth, okay? We're going to talk a little bit about those. This is a transcritical system, okay? Everything in red, for those of you that didn't join us a couple weeks ago or didn't see Andre's presentation, this is where we're going to see our high pressures. When we first started out, that was typically always stainless steel. In a lot of cases, it still is. There is some high pressure copper out there. It's called XHP, extremely high pressure copper. That's only one brand that I know of. It's made by Mueller, okay? A couple things that we talked about 2 weeks ago. You're going to start to see a few new items here. One of them is going to be this high pressure valve, okay? So we're going to hold back that pressure. Now it's going to be tied in with our high pressure controls here. So when it's in transcritical, this is going to be working with, in conjunction, back to our E2, and it's going to be trying to do the best COP that we can for these compressors, okay? So when the temperature rises outside, above that 88 degrees, this will be reading our COP, okay? Trying to work in conjunction back here to run them as efficiently as possible. Now, if it gets out of hand and it has to release more gas as the temperature rises up, it's going to go into our flash tank, which is nothing more than a beefier receiver, if you will. It's a storage vessel. And then you see our bypass valve over here. And what it's going to do is try to keep this stable, somewhere around 550 or so. And when I crunch the numbers, if you have the PT Pro and you look at CO2 on the PT Pro, 550, 600, somewhere thereabouts, you're looking at 39 degrees or something. So we're trying to keep this stable around that consistent temperature or pressure, so we get this a nice line of liquid column into our metering devices and keeps it stabilized. So we're actually going to blow that off into this header. So if you look at this, we have 3 different suction pressures coming into this one header, feeding in our medium temperature compressors. Back to this, when we're in subcritical, this is going to be reading subcooled liquid, okay? It's not going to be reading our COP, okay? When we're transcritical, it's working in conjunction back here to keep these as efficient as possible, all right? going to walk through this one more time for you, those of you who didn't see this a couple weeks ago, and I'm going to go through this fairly quick just to walk through it. Here again, we're going to our compressors and our transcritical, coming across to our condensers, going down through our metering device or our high pressure valve, coming across to our flash tank. Again, we're releasing some temperature there, going down through our first metering device at the medium, coming across in the evaporator of the medium temperature, going down to the metering device through the low temperature application, coming across to our bypass valve, down through our metering device, going into the header, coming across through our evaporator and our low temperature to our ZO compressors, and then up through the ZO compressors, our low temperature CO2 compressors at the bottom, our scrolls. Okay. Again, we're going to use all electronic centralized controller, transcritical compressors, subcritical compressors, VFDs. Everything's going to be variable. Again, we're going to have all electronic controls. Okay, very hyperactive CO2, fast moving. Andre actually showed this picture also earlier. This is a system in Atlanta, Georgia, okay, of a transcritical booster, by the way. And you know how hot Atlanta is. So above 88 degrees, we said earlier that CO2 doesn't do so well. You can see our medium temperature at the bottom and our low temperature at the top, our scrolls. We have software. Any questions on that so far? I guess we'll take them as we go along. Strategies for high warm ambient operation. The whole objective here is to bring these two lines together, okay, as much as possible. Make that equator, if you will, smaller, okay. It used to be said that if you ran below 50 degrees, for the most part, primarily most of the year, you could use a transcritical system. Now we say that if you run up to 60 degrees, so it's getting more efficient and more the different things that we're doing, like adiabatic and different things, we're bringing that line closer and closer. For the most part, this is subcritical CO2. When we say subcritical, what we're saying is these are primarily, mostly DX systems, for example, okay? So we would have an HFC at the top, okay, and an HFC and a CO2 at the bottom, okay? So that's what they're talking about when they're talking about subcritical CO2. Up here, we see transcritical and subcritical. Again, why would you have transcritical in these cooler areas? Because they're using that water, that transcritical, that discharge temperature for reclaim, whether it be heat, humidity, or water. A lot of your fish areas, meat, and those kind of things. A lot of sanitation. They use a lot of hot water. Down here again, same thing. Subcritical would be your HFC up on the medium temperature. Transcritical, they're pushing it transcritical to utilize some of that heat. 4 ways of improving efficiencies in warm ambient regions. I'm going to go through these one by one. We have parallel compression. We have adiabatic, which is nothing more than either spray nozzles and evaporator adiabatic coolers. And then we have a mechanical subcooled braze plate, and then we're going to talk about the new kid on the block, the ejectors. Okay. Parallel compression. Parallel compression is nothing more than we've got a braze plate heat exchanger here, and we're taking one of the medium temperature compressors and making it much smaller. So we're coming in with a higher pressure, higher temperature, which puts less work on this. Instead of coming through and just blowing it off on the bypass valve and sending it into the header, when that high temperature gets high outside there, above 88 degrees, we're now utilizing it, removing some of the heat here, bringing this down and adding some of the heat actually, and raising the temperature higher up here, which makes it more efficient. We talked about, I think Ed and Kevin talked the other day about a few weeks back about raising that suction temperature, pressure, and we talked about the efficiency by raising the suction pressure. 1 psi, you gain approximately 2% in efficiency. So you can see over here where we're starting out, what temperature we're starting out with a normal compressor, okay? And you can see by raising the temperature how much higher and less work we're doing on that smaller compressor. The higher gas density of the CO2 results in a smaller compressor, usually about 8 to 10% higher annualized efficiency, much smaller gas cooler, okay? And this is just a blown up picture of what we just saw earlier. The thing I wanted to point out here, and I think Andre touched on this earlier, is you can see the difference in by raising that temperature, okay? How much more BTUs we're getting, 236 over here on the smaller compressor by doing this, the benefit of doing that. So basically, if we didn't have this and we had 10 compressors there in the wrong time of the year, meaning that it's above 87.8 degrees, you might be loading up half of those compressors, 5 of them, by just loading them up with gas blown off by the bypass valve, which obviously is very inefficient, okay? By using this technique, we can load up at a higher temperature, higher pressure, and get like a higher pressure of 578 compared to a 427, and you can see what that does for your BTU capacity. Opportunity exists to downsizing the parallel compressors. We can talk about adiabatic gas coolers, which to me, if you visualize like a swamp cooler or a really almost like a residential humidifier, if you will, okay? So what the adiabatic is doing is running these panels on the outside with water, and I actually put an actual system in one of those slides last night to give you a better visual. These systems utilize a mesh suspended in front of the coil or the condenser face. Possibly a nozzle is used to direct it towards the mesh. Water is sprayed. There's several different designs, okay? We talked about earlier, this is when we're in subcritical, this is a condenser, okay? We can condense that refrigerant. When we're in transcritical, it's a gas cooler, okay? We're still removing heat, but we can't condense the refrigerant because now it's in supercritical fluid, okay? All right? So the idea of this is for this condenser to see a lower temperature. So for example, if it was 90 degrees outside, it's going to see 85, okay? We're bringing that down by cooling this, bringing the air through that adiabatic cooler. We're bringing that temperature down somewhere between 15 to 20 degrees. The adiabatic cooling relies on the difference between the ambient air dry bulb, the temperature, and the wet bulb temperature, about 2 degrees off the wet bulb typically, okay? This is actually one of those systems I thought would be a good visual for you. So this is a pump inside here that's recirculating that. You can see where we're tied in here. And again, these are our pads on the adiabatic cooler, okay? So as the air draws through. Now, this won't be on if we're below 88 degrees, okay? If we're not in what we would call transcritical, the medium temperature part of that application, this water won't be pumping because the air is fine where it's at, all right? It's only going to turn this circulating pump on or this water on when it indicates that it's above that 87.8 degrees, okay? It manipulates that. And this is just an example of our software, our PSS software. You can see here hours in the year, obviously. Without adiabatic in Atlanta, Georgia, we're running somewhere around 1,020 hours with a gas cooler. In other words, transcritical, okay? As opposed to Toronto, which is using about 202 hours. By adding our adiabatic cooler on the system we actually installed in Atlanta, and I'll show you that here in a little bit, I believe, we went down to 9 hours a year with the adiabatic cooler. That's obviously a huge savings. So really, the temperature outside, what this is doing is this is figuring up, this software is figuring up how many hours we're using this that we're going to be above transcritical or above the critical point, okay? So people don't take into consideration how many hours of the year, even if it's typically hot outside in the summer, very hot, how many hours of the year that we're talking about below that 80 degrees. We're talking about evening, fall, winter. You'd be surprised how many hours you actually can utilize CO2 in the system, okay? A lot of times when they're using adiabatic, they'll also use the parallel compression in conjunction with it. Not always, but sometimes they will use that. So we're still using a smaller compressor here, which is using less energy on gas that we typically would be blowing by anyways, loading up, nothing more than loading it up and not utilizing it for efficiency. We're going to talk about mechanical subcooling now. Mechanical subcooling is nothing more than using a mechanical subcooler. Let's take, for example, here, we're putting this in the system. So we're using this, let's say this is 134A or 513, whatever that is, and we're using that mechanical subcooler to cool the CO2 down. So in other words, the farther that we said earlier, this is our compressor, this is our condenser, we're rejecting heat. By using this mechanical subcooler built in here with 134A, a small amount of refrigerant or HFC, okay, we can make that line go over further in our heat rejection, okay? And the further we go over, the more subcooling we increase that capacity. It also increases our EER value, okay? So this is one technique that they're using also. Now we're going to talk about what most people are talking about is the new kid on the block. It's not really all that. I had a hard time at the beginning a few years ago, or 2.5 years ago now, when I first started training under our Canadian team and different people that work around it. They're much further ahead of us over in Europe, about 17, 18 years now, and Canada was also, but as I'll show you how many systems are going in the States as we move along, we're catching up. Not only catching up, we've passed Canada now in the last 6 years, so that's a good thing. But here's how the ejector works. We have the high pressure gas coming in from here. The high pressure gas is approximately, let's say, 1200 PSIG. The suction gas we're using is around 407 PSIG. We're removing this vapor. Instead of loading this up again, we've got a much less pressure, less temperature here. We're coming back and running it through the ejector, okay? This is like a supersonic coming through here, which opens it up and pulls this down, okay, into this flash tank, approximately 500 PSIG, as I said earlier, 550, somewhere thereabouts, okay? So what it's doing is mixing the gases, the two, cooling this down, keeping it a little more stable, but it's also taking more work off of this compressor, these compressors, our medium temperature compressors, and utilizing gas that we've already compressed and bringing it back in again, okay? Here again is the models we talked about at the beginning, our medium temperature and our Zoe, our low temperature compressors. These are actually on our trainers that we use all the time. Andre mentioned this earlier, and I don't brag it up enough, and I should, shame on me. When we have our trainers out in the field, it is very, very common for people that have used our competitors' compressors, and I'm not exaggerating one bit. It's a given every time we fire our CO2 trainer up that if they've worked around one of our competitors' transcritical compressors, without a doubt, they are going to comment on how quiet up close our medium temperature compressors are. It is amazing. We can stand in front of them and literally talk and hold a conversation like we're doing right now. There's no yelling, and I'm not kidding you. Every time we fire this up, people typically will have to reach out and touch the compressor. They can't believe that it's running. Until they feel the small vibration, they are shocked. It is mouth-dropping to our customers when they see this. So something to brag about. obviously, as we always tell them, and they bring it up to us, it's a little more expensive, but it is amazing the difference in the quality and the sound that you have on our compressors. And Julie, that's all I really had today. And for you, those of you that joined us from Emerson, again, I apologize. I don't really apologize. I didn't realize what Andre was going to do, and he didn't realize what I was going to do. We talked a little bit, but we didn't really talk about what we were going to present today. So it was eerily familiar. When I saw his presentation, I thought, you're going to be let down when you see mine, because it was basically the same thing. So that's all I've got.
Not at all. Thank you, Don. This is not simple, not necessarily simple content to understand, and for those of us that are not technical by nature, it certainly helps to hear it more than once. So definitely appreciate you taking the time to explain it to us. I have not seen any other questions pop up. For those of you that are on the call, you'll give you about 20 minutes or so of your day back. At 12:30, we'll be getting on. And for those of you that are wholesalers, it'll probably be more relevant to you. I know there are a couple of contractors potentially and end users that have been on here, but we're going to have Roger Miller go over some of the portal enhancements and features since the launch of the portal, now close to 2 years ago. So we'll be doing that at 12:30. If we have time, Mike Nipper is going to go through the OEM wholesaler program. And then tomorrow, the invitation already went out. You should have received it. We're going to have Otto Spiederman from the air conditioning group talking about HVAC, commercial scroll and HVAC systems. And then I believe on Wednesday, we're going to bring Scott Abeni back, and he is going to do more of an in-depth overview and training on Co2 Mobile. We did a high-level overview a few weeks ago and got quite a bit of interest. So I'll be sending the invitation out for that here today, and I would encourage you to go ahead and share that training invitation, not just with your organizations, but please push that out to any contractors or end users that are Co2 Mobile users or that would be potential users. The more people that we can get invited to that, the better. We definitely want to propagate Co2 Mobile out there as much as we can. So again, thank you everybody for dialing in, and have a good day.